Good morning. Today we're going to talk about section 4.7, L'Hôpital's rule. And this might be your first foray into the French language. But this little H-O with a hat combination makes the hard O sound. So this is pronounced L'Hôpital. Not La Hospitals, not L'Hôpital, but just L'Hôpital. And we're going to talk about his rule and what's going on with that. So while it might not make any sense, we are going to bring it back to limits. And chapter 4 is really about, now we have this idea of the derivative, now we can use the derivative. What can we use the derivative for? And this is one of those examples where we can use a derivative to make life a little bit easier than it used to be. So in chapter 2, we discussed limits a lot. In fact, that's nearly all we did, but we didn't do it exhaustively. And some limits posed greater challenges than others, like the limit as x approaches 0 of sine of x over x, or the limit as x approaches infinity of x over x plus 1. Simply plugging in our a value left us with 0 over 0 or infinity over infinity, which are indeterminate forms. And sometimes we're able to factor polynomials and divide or multiply by reciprocals, but often we can't do that. And we need special techniques to determine what the value of the limit is. And a particularly powerful technique is L'Hôpital's rule. And you guessed it, L'Hôpital's rule has to do with the derivative. So this is for the indeterminate form where we get a 0 in our numerator and a 0 in our denominator. So suppose f and g are differentiable on an open interval I, containing a point A with g prime of x not equal to 0 on I when x does not equal A. If the limit of f of x and the limit of g of x both equal 0, then we can say that the limit of x approaches A of f of x over g of x is equal to the limit of x approaches A of f prime of x divided by g prime of x. And this it doesn't make any intuitive sense. There's no way that you look at a graph and you look at it and you say, yeah, the limit of the ratio of these two functions is equal to the limit of the ratio of their tangent lines. But indeed it's true, and L'Hôpital worked really hard to prove that. So now we get to use this fun little fact for free. The rule also applies if x approaches A is replaced with x approaches plus or minus infinity, or x approaches A from the left, or x approaches A from the right. So we can really use this tool to our advantage. Speaking of using tools to our advantage, let's go ahead and jump in with a few examples. So let's evaluate the following limit. The limit is x approaches 1 of x cubed plus x squared minus 2x over x minus 1. When we plug in our a value of 1, we get 1 plus 1 minus 2 over 1 minus 1. So we get 0 over 0. So we need to do something else. And if this was still chapter 2, we would probably factor and eliminate an x minus 1 from the top and an x minus 1 from the bottom. But here, we can do something a little bit easier. And maybe you don't believe me that taking derivatives is easier than factoring polynomials, but trust me, when polynomials get nasty, taking derivatives is really easy. So we're going to use something else. We're namely going to use L'Hôpital's rule. So we're still trying to evaluate the following limit. So we're going to first start by determining what is our f of x and what is our g of x. And here it's really simple. Our f of x is the numerator, x cubed plus x squared minus 2x, and our g of x is the denominator, x minus 1. And then we take the derivatives of each. So f prime of x is 3x squared plus 2x minus 2, and g prime of x equals 1. And we just want to make sure that our derivative g prime exists everywhere on our interval, and 1 exists everywhere, so we're good to go. Now we can evaluate our new limit. So 3x squared plus 2x minus 2 over 1, we plug in 1, we get 3 plus 2 minus 2 over 1, which is just 3 over 1, which is 3. And if you want to go ahead and double check, you can factor our original polynomial into x times x minus 1 times x plus 2 over x minus 1, get rid of a few things, and you'll see that we have the exact same answer. So L'Hôpital's rule works, and it's much easier than doing something else, especially when what we have is not a polynomial. So let's check another example. Now we've got something where we need to evaluate this limit using L'Hopital's rule. So that's a big hint that I'm going to get 0 over 0. My first step is I'm sorry, I understand what I wanted to do here. I wanted to give you this as an example for you to work on. And just know, this is an example for you to work on. The answer should be 1 over 2. So go ahead and work on this example, and if you don't get 1 over 2, email me and we can work through it together. Now, let's talk about another example. This one is evaluate the following limit, the limit as x approaches 0 of e to the x minus 1 over x squared. The limit has the indeterminate form 0 over 0, so we must use L'Hopital's rule, which gives us the limit of our original function becomes the limit as x approaches 0 of e to the x minus 1 over 2x. And we can tell that when we plug in 0, e to the x becomes 1. We have 1 minus 1. Oops, we've got a 0. Over 2 times 0, which is 0. So we've got 0 over 0 again. Well, what can we do? And the answer is we just have to apply L'Hopital's rule again. So we apply it one more time and we get just e to the x over 2. And when we plug in 0, we get 1 over 2. So yes, you can apply L'Hopital's rule more than one time, but in order to use L'Hopital's rule a second time, you must establish that your new limit is indeterminate. It wouldn't make sense for you to use L'Hopital's rule once, get something that was just an answer, not an indeterminate form, and then use it again. So you have to make sure that there's a reason why you're using L'Hopital's rule in the first place. So now let's talk about another indeterminate form, infinity over infinity. Suppose f and g are differentiable on an open interval I containing a point A, with g prime of x not equal to 0, on our interval I when x does not equal A. If the limit of f of x and the limit of g of x, both of them equal plus or minus infinity, then the limit of the ratio of those functions is equal to the limit of the ratio of their derivatives, provided the limit on the right exists. The rule also applies for x approaches plus or minus infinity, x approaches a from the left, and x approaches a from the right. So let's do a quick example. And this is actually going to be an example for you to work on because I think it's pretty straightforward. Verify that the following limit results in an indeterminate form and then use L'Hopital's rule to evaluate the limit. So for this one, you should get that the limit equals 2. And of course, this is one of those ones that we can verify by just saying, oh, because we have x cubed in the numerator and an x cubed in the denominator, we can just use their coefficients. So 4 divided by 2 is 2. Or you can use L'Hopital's rule to guarantee it. And that's going to be it for me today. Well, not completely. That's it for video 1 today.